This week we start to discuss trees. I have here a PowerPoint presentation that I have put in the module. So what do we think about when we think about a tree? We think about a collection of nodes that can hold data, and they are joined together in some way so that we can get from one to another. We can hold data in these nodes just as if it were a linked list, although this is a more complicated linked list. Instead of a head, we call this thing a root. And the ones at the end we call leaf. So in this particular tree, I have one root. I always have one root. Here I have 1, 2, 3, 4, 5 leaves. I can have more. So I'm not really obeying too many rules here, except that I have a starting point, which is a root. From there, I can travel to other nodes in my tree, and the ones on the bottom are called leaves. On the bottom meaning I can't get anywhere from there. So in this case, I have 1, 2, 3, 4. I have 5 leaves. This is a general tree. It says here, definition of a general tree. A set of one or more nodes, T, that's the tree, is partitioned into subsets. We've got the root, and then on the left here, this is actually another tree with its root here, and to the right this is another tree with the root here. So that's why it says subtrees. A root has no parent, and this is where we kind of get this mixture of ancestors, like family trees, and trees that grow in the yard which have roots and leaves. So and an upside down one, because the root is always on the top and the leaves are always on the bottom. So we've got roots and leaves. This node here, this root, has 2 children. In this case, 2 children, a left child and a right child. This particular left child has itself 3 children, and this one here has 2 children. These have 1 child each, and if you look at the leaves, they have no children. So for any general tree, a root has no parent and the leaves have no children. A leaf, this leaf, the parent is this one, this node, the parent is this node, the parent is this node, the parent is the root. The root is the only one that has no parent, and the leaves are the only ones that have no children. So this is a general tree. Not a binary tree, a general tree. A binary tree, each node has at most 2 children. So this is not a binary tree because this guy here has 3. But if I got rid of one of them, let's get rid of the middle one, which is the easiest to delete. Okay, now this is a binary tree. It's a binary tree because each node has at most 2 children. We have to say at most because leaves have no children. You can see here these nodes have only 1 child each, but this node has 2, this node has 2, and the root has 2. So again, a binary tree has a root, and any node has at most 2 children. Here we have a binary search tree. It's a binary tree because each node has at most 2 children. That's the definition of a binary tree. A binary search tree is a tree where anything that is less than a node is to its left, and anything that is bigger than the node is to the right. So here our root is 10, 17 is bigger than 10, so it is to its right. 4 is less than 10, so it's to its left, but 7 is bigger than 4, so it's to its right. And 1 is less than 4, so it is to the left of 4. In the example over here, it's got strings. Jane, the string Jane, is in the roots. Bob is less than Jane because if I used the compare to with strings, Bob would be less than Jane. B is less than J. Alan is less than Bob. A is less than B. Ellen is bigger than Bob because E is bigger than B, etc. So this is also a binary search tree, but binary search trees don't have to have this beautiful shape. They can have this shape too. For that matter, they can have this shape. This is also a binary search tree because any node has at most 2 children. That makes it a binary tree. And then 4 is less than 10, so it's to its left. 1 is less than 4, so it's to its left. And therefore this is a binary search tree.